Thank you very much. So I will continue in some part or in some extent the previous two papers or the previous two lectures. And I would first outline a model which was elaborated for general fields, but I will specify it in this presentation to the electromagnetic interaction. So what are the symmetries beyond the standard model? So as we heard, the standard model was developed and completed in the 1970s, and it turned out to be a very round and very perfect
So the first part of my presentation will what does mean the isotopic field charge and spin. About a little of the history, the idea of the isotopic field charge or the field charge model was born in January 2001, and I started to work on this model in the next years. I discussed this model in 2002 with György at the Wiener Centenary Conference, which was held in Page, then in 2003 at the first Symmetry Festival, when Larry Wood, our chairman, participated in the discussion with György, and it was followed with a long discussion in writing correspondence with György until his death in 2005. Then I first published the mathematical model, which based the mathematics of that physical model that in 2011 was published first, and then I started to specify the model to the gravitational interaction and later to the electromagnetic interaction, what is presented now here. So, what are the roles of the symmetry principles in the history of the scientific thinking? In 1995, at one of our previous meetings, similar meetings in Washington, D.C., I sketched the world view by Herodotus, according to which the facing symmetry of the world was stronger than what was actually experienced. And all in the history, when a decision had to be made between facing symmetry and empirical experience, the advantage was always given the former. So Kepler was the first person in the history of science who was able to abandon his deep faith in the harmony of the universe. So a dominant belief which was followed also in the 20th century was that one could find explanations for new phenomena through symmetry principles, and one meets with the evaluation of a non-symmetry. One believes that the violated harmony in the world can be restored by another symmetry. By another symmetry that was hidden at a deeper level. So such beliefs hold even in the 23rd century. Let me extend very shortly what Professor Kuft explained us about the spin, because the isotopic field charge spin theory is something like the spin, so let me start the explanation with the spin. The Pauli exclusion principle, which introduced the notion of the spin, was formulated in the second part of the 1920s, so more than 90 years ago, and it ascertains an observation that two fermions, that means the half-integer spin particles, cannot be in identical states within the same system. But what is that spin? The spin is the half-integer hidden property of the particles, which cannot be observed, but it is a mechanical, abstract, and a conserved property, which is to be added to the angular momentum of any particle. So it is an extensional abstract property, and its conservation represents the invariance under abstract rotation expressed by a transformation group called the S2. The conservation of the spin, like any conservation laws, predict new particles. So happened with the assumption of the spin by the end of the 1920s, and I will show a picture to you what would happen with this idea, or this prediction, which today by it starts, if our predecessor physicists when they would use the Facebook at that time. So it would happen at the one machine that Wolfgang Pauli would announce that he needs a new particle to make his theory work. So he predicted a particle, but that particle, which later was called the neutrino, was not found. It was found only many years later. And you can see here the correspondence on the Facebook between the greatest personalities of physics of the 1930s up to the 50s and up to the 60s. Even Peter Higgs would have a doubt about the neutrino, and because he has not the best experiences by finding predictive particles like this has not been found for 50 years after his prediction. So we always can be very cautious when a theory predicts a new particle, but we are very much certain that when the theory predicts a particle, then the physicists will later or sooner or later find it. So in all cases, when a new physical phenomenon presents itself, we assume that the Pauli exclusion principle holds true. And this means that we can extend the Pauli exclusion principle, we can make an extension to the interpretation of the spin, and we can make an extension to the Pauli principle. So how does it work? First, the Pauli exclusion principle was formulated to electrons. We now use it to other fermions and field charges, and beyond the electromagnetic interaction, we assume that the Pauli exclusion principle works for fermions in other interactions as well. So, in the future, we used to consider all spin-like, all fiber conserved quantities whose conservation is ensured by the invariance of the same symmetry group. But those rotations are no more interpreted in the space-time. Those are like we saw in the case of the isotopic spin or isospin in abstract fields. So for the rotations are executed in abstract fields, those spin-like quantities are no more mechanical character. So there are such indistinguishable particles like we saw in the first presentation, like the proof of the proton and the neutron, which cannot be distinguished under the effect of the strong force, but we know that they may transform into each other, they may exchange charge, and may be considered as isotopic states of two identically considered particles. We consider that there are certain hidden or hypothetical properties, and such a hidden, earlier hidden property was the isotopic spin, which turned out to be a conserved property, as we saw in 1954. Shen-Yin Yang and Robert Mills proved the existence of such a conservation theory, and which predicted such a field which was not renormalized for many years, but the renormalization of the field was made 17 years later, partly by our first speaker, Professor Hooft, and his teacher Weltman at the Utrecht University. And this paved the way to the interpretation of the Higgs mechanism, about which we heard very much. And this was a good initial to interpret the interaction between the quarks and the introduction of the new property or my graphic artist friend Tamás Farkas, and me, you see here the three represent the three quarks, and the three quarks change permanently boson colors, and there are the gluons which mediate the exchange of the color charges between these particles. So let me specify our interest for the electromagnetic interaction. Too much light here. I prepared my slides for a dark room. So I use black color and light color. So there are the red and the two red particles which theoretically approach to each other from the infinity in different directions, and they will interact when they will get close to each other. At the end of the 1920s and in the early 1930s, there were elaborated two perturbation models for the so-called quantum electrodynamics. One of the models which was followed by Paul Dirac, which can be found in most of the textbooks around the world. When first the scalar potentials, that is the Coulomb potentials of the two electrically charged particles interact, and they will interact the electromagnetic fields. And there was another model elaborated 2-3 years later, that first the fields interact and then the scalar potentials will interact. And the second interaction was considered in both cases as a perturbation. The perturbation for non-physicists, participants of festival means a certain approximation in mathematical physics. So very soon, Bethe and Fermi will show that the two approaches are equivalent. But then there was a problem to which they didn't pay enough attention. That problem was that there was an asymmetry in the scattering matrix in Christian Müller's model, who applied the second part, means according to his model, first the fields interact and the interaction of the scalar potentials was considered as an approximation. And Bethe and Fermi solved this problem so in a paper that they artificially symmetrized this element of the scattering matrix, what I will show later, and didn't pay attention to the difference between the roles of the two interacting particles. So, if really the scattering matrix of two interacting electrically charged particles contains an asymmetric element, then it is a sign that the roles of the two particles interacting should be distinct in some property. So, this led to the idea of the isotopic field charges. That means that we consider that the two interacting charges always differ in certain, until now, hidden property, and we consider these two charges as isotopes of each other. And field charges are in all interaction field. In the gravitational field, we call field charges the mass unit, but we do not found it. It's very small. The electric charge, the big charges, the color charges, they are the respective field charges of the interaction fields. And these field charges, which are introduced in all textbooks, appear always in the scalar part of the scalar field, like sources of the scalar field, occurring in the energy function, that means in the Newtonian of the interaction field. The isotopic field charge charge are those partners of these sources of the fields which appear in the vector, in the kinetic part of the potentials, that means in the vector potentials. They were not distinguished earlier. Now we make a distinction between them, but we didn't know what property do they differ in. Is this something different, something different hidden there, or we knew about it, only didn't pay attention to it? So it was born the idea of the isotopic field charge speed. So when we interpret the electromagnetic interaction model sketched by Christian Möller, that means an asymmetric model between the asymmetric role between the interacting charges, the roles of two interacting electric charges are not equal, and they must differ in certain characteristics. So this led us to an assumption that similar to the Pauli exclusion principle, they should be different in a spin-like property, and since they are called the isotopic field charges, let me call this still hidden unknown property the isotopic field charge speed. We can see similar differences between the charges in the gravitational model. For centuries we know that we have gravitational and inertial masses, and we can consider them as isotopes of each other. We know that the mass of gravity and the mass of inertia are equal, but are not identical. I will not tell too much about this because in 2006 at the second Symmetry Festival I gave a lecture about this. So they are qualitatively different quantities because the equivalence doesn't mean an identity. So the mass of gravity and the mass of inertia are isotopes of each other, and they are the isotopic field charges of the gravitational field. And the mass of gravity appears in the potential part of the energy function, the Newtonian, and it is localized in the space-time, while the mass of inertia appears in the kinetic part of the energy function, but the energy function, the kinetic part of the energy function is always something velocity-depending quantity. So the gravitational mass is localized in space-time, the inertial mass is localized in a velocity-dependent field, and this calls to the assumption, that we need a kinetic gauge field in order to describe this interaction between the two kinds of particles, between the two isotopes of the gravitational charges and the other ones. And this is described by this D field, which is a kinetic field or a velocity-dependent field which depends on the space-time coordinates on an indirect way. So, the scalar potential mass and the kinetic mass, the mass of inertia appear in the two different parts of the energy function, and that happens something similar with the electric charges. The so-called Coulomb charges or the scalar potential, isotopic electric charge, is not identical with those current-like charges which appear in the Lorentz force and what we call the kinetic isotopic electric charge. If we put these charges, instead the charge densities and the charge current density, you see in blue there appear the kinetic charge densities, and in yellow there appears the Coulomb type charge density. So they appear in the two parts of the potential. according to the covariance principle, which holds everywhere in our physical world, they can transform into each other when we change to another reference frame. That means they must be invariant under the Lorentz transformation. So there is an exchange and invariance between them when we switch the two charges. But the question is whether this transformation is enough. Why must we put this question? We must put this question because the constructed current, what we see here, distorts the Lorentz invariance of our equations. If we put the two types of charges or charge densities in the currents, our equations are no more Lorentz invariant than itself. So in the isotopic field charges are different physical quantities. They can probably interact with each other, and this is surprising because we have not experienced nothing similar in our physical experience. If the isotopic field charges are different physical quantities, they distort the Lorentz invariance of our vectors and tensors, and they distort the covariance of our equations, and this is even more surprising. So this not only contradicts the experience, but it is unacceptable according to our traditional physical picture of the world, and this is unacceptable at least in the standard model, but not in the presence of the conserved isotopic field charge speed. So in 2009, I showed that the isotopic field charge speed is can be proved mathematically as a conserved quantity. The mechanism how they can switch between each other is the following. You know that if we have a ball, and I drop it, in this position it had a potential energy, and at the floor it has a kinetic energy. Of course, if I put it higher, it has more potential energy, and at the lower level it has much more kinetic energy. But this consists of many mass units, and these mass units are in a mixture of potential and kinetic states. But if we consider this ball a single mass unit, which is so small that we cannot demonstrate it, then it is now in a potential state. Then it drops and exchanges a state with one of the mass units of the Earth, and it will get into the other position in a kinetic state and back. The Earth, which consists of many mass units, will not observe this exchange, but our single unit mass will experience this change. But since our ball is a real ball, it consists of many mass units. That means it is a mixture of potential and kinetic state masses. But when it is on the floor, there will be in this picture more kinetic state particles and less potential state particles. Something similar happens in the exchange of the electric charges as well, and this is reflected in the scattering matrix written by Christian Möller in the interaction of two electric charges, and you see here the asymmetric component in this scattering matrix. So we have the closed asymmetry. The charge current loses its symmetry under Lorentz transformation, and so the whole equation describing our physical laws in the situation is similar in the gravity and other interaction as well. But our physical laws must show up in unchanged forms in any reference frame. The Herodotian picture of the world suggests us that we must conjecture that the most invariance must be restored restored by a certain complementary transformation by means of an additional U invariance. The south U invariance was the conservation of the isotopic field charge spin, which were demonstrated by me in two papers 3 and 5 years ago. Applying the isotopic field charges in the presence of a kinetic gauge field, we have not one, as in classical field theories, but two conserved Noether currents. The first Noether current, conserved Noether current, provides us the conservation of the field charges, those field charges which appear in the potential part of the Hamiltonian. And the second conserved Noether current will provide us the conservation of the isotopic field charges. This leads to the result that our physical equations are invariant under the joint application of the Lorentz transformation and another two-parametric simple unitary transformation which corresponds to the transformation and conservation of the isotopic field charge spin, and it is this combined transformation group. This corresponds to this describes the Lorentz transformation, and this describes a spin-like transformation. So, how could we keep the physical relevance of our theories? We accepted the distinction between the two isotopic field charges, but we cannot accept the distortion of the Lorentz invariance of our vectors and tensors, and we cannot accept the distortion of the covariance of our equations. So, along with the assumption of the existence of the two isotopic field charges, we assume a hidden additional invariance which can transform the isotopic field charges into each other, and if we apply this together in the Lorentz transformation, this makes our vectors and tensors invariant under a combined transformation, and this restores the covariance of our equations. So for 100 years, we strongly believed that the Lorentz transformation is that transformation which holds for all our physical theories and for all our physical variations. But it is never written in the nature's book, that it should be only the Lorentz transformation which should be responsible alone for the covariance of our equations. So we extended our theory with another transformation, and this combined transformation holds in extreme conditions. How can we interpret the isotopic field charge spin? We know that it can take two values, namely potential and kinetic values, how they can transform into each other. They are invariant under a group of rotations in a kinetic field. They have two stable states that they can take up in the course of the rotation, and this rotation corresponds to an assumed group like a spin. And according to a convention, they can take the values which we establish as half and minus half integer units. The two conserved Noether currents ensure the conservation of two physical quantities, and the first coincides with those which we knew. The second new conserved current guarantees the conservation of the isotopic field charge spin, and since any conserved property presumes the existence of a mediating boson, a mediating boson, what we call the dion, must belong to each isotopic field charge spin pair as well. So the interaction mechanism conjectures the existence of two mediating bosons. The standard model bosons which we use, and these 13 bosons are responsible change of the spin, and the pions you presumed bosons which are responsible for the exchange of the isotopic field charge spin. Two fermions always in opposite isotopic field charge state can interact. And if they can, they will do. In contrast to the supersymmetric model, the isotopic field charge spin model presumes fermion-fermion and boson-boson pairs. This is the difference picture gives. The fermion pairs were actually in four. You think about the gravitational inertia and the inertial masses, the Coulomb time charges and the Lorentz time charges and so on. And only we have not taken into account them and have not made a distinction between them in our physical equations. The predicted 30 new bosons need to be demonstrated in experiments. They are even less found, less extent found and sound than the supersymmetric particles were. So in the rest of my time, I will speak about the isotopic field charge spin model applied to the electromagnetic interaction. We will start from the Dirac equation as we did from this equation and this quadratic form. And in the first step, we will replace in this equation the general mass with the gravitational and the inertial masses. This was unusual earlier in our physical equation, but why not to do that? Okay, first. So you see the two kinds of masses inserted in the equation in green. In the following slides, I will show a lot of equations. Don't threaten about these equations because they will appear for many of you very difficult and complicated. Pay attention only to the colors of the different components of these equations, because I marked with colors the difference between the classical 90 years old classical quantum electrodynamics and between the isotopic field charge spin model applied to the electromagnetic interaction. So, in the second step, we will replace the general electric charges with the two isotopic field charges or charge densities. Rho will replace with the kinetic and with the potential and the kinetic field charges. And you see now in blue and green in the both equation appearing the charge densities and the masses. So let me bring into this form, we made certain multiplication and put in the equation the respective operators. And you see the upper two lines in yellow and the brown line, the third line in the bottom. The brown line shows what is the new component in the Dirac equation, but it contains as a limiting case the original Dirac equation as well. As a third step, we extend the electromagnetic field with the kinetic field. As I mentioned, we suppose that we must have an additional kinetic field, and with magenta you see the appearance of the kinetic field in this equation. And now we execute the multiplication, and we get the full extended Dirac equation. It seems very complicated. It consists of 5 lines. The first 2 lines coincide with the original Dirac equation, and there are 3 other lines below which are the new components of the Dirac equation. Let me analyze these 3 situations. First, let me see then the difference between the kinetic and the potential masses is very small. In this limited case, we can neglect the last three lines and we get back the original Dirac equation. That means in a limited case, we are at the standard model. What is the situation when the velocities and that means the energies are very high? This means the kinetic mass is according to the Lorentz increase of the mass with the velocity is much larger than the rest mass. Then the quantities of the first four lines can be neglected, and there holds only the fifth line of the Dirac equation, and I will show that it turns into the Schrödinger equation. There is a medium situation when the kinetic mass is much larger, than the potential mass, but not too much larger. In this case, the third and the fourth lines get significance because this will provide us contributions to the magnetic and electric moments. We will discuss them also if I will have enough time. So, I would like to speak about, there are many consequences of this theory. I would like to concentrate now to four issues. The first two issues for the quantum mechanics. The theory offers the extended Schrödinger equation that follows from the extended Dirac equation, which was not the case in the classical quantum electrodynamics. And the second, what I will discuss, that the theory keeps the electron's wave function from spreading out too far, because the frequent periodical exchange between isotopic field charge states prevents them from running away during the short period between the switches of the state, between two switches of the states. For the macroscopic electromagnetic phenomena, this equation provides the interpretation of the electric moment that the classical Dirac equation could not handle. And the fourth is for particle physics. It predicts the muons as intermediate bosons, which can be alternative to the supersymmetric particles and are in as much accordance with the standard model as is the Susie's theory, at least theoretically. So let's see the first case, the derivation of the extended Schrödinger equation. In how many times I have? Enough? Okay, then I continue. So let's concentrate now on the below the fifth line of the extended Dirac equation, and the multiplier of this expression looks like this. And if we replace P4 this operator, we can get this equation. In this equation, and I put this on the left side, and here there appear the different isotopic charge densities, and there appears only the rest mass, which is identical with the potential mass. And this expression corresponds to the energy of the system, so it can be replaced by the Hamiltonian operator, and we get back just the classical Schrödinger equation, which follows now from the extended Dirac equation. What about the runaway phenomenon, which was predicted and was a problematic thing in the classical quantum mechanics since the 1920s? According to our model, the charges can interact if one of them is in a potential corpuscle state and the other in a kinetic, means a Wavelet state. In interactions, they compose a common system, as we saw in the model, On the basis of the Pauli principle, it is plausible that they must differ in at least one of their properties. Since they are in principle indistinguishable, this distinction should be made here in the isotopic field charge or the isotopic field charge spin. They exchange a photon and they exchange a dion parallel during the interaction. The photon switches their spin and the dion switches the isotopic field charge spin into the opposite state. So the way about the wave corpuscle duality, we have no time, we didn't allow enough time for the electron to run too far away and to get too large, at least in a bound state of 2 electrons or more. And the other charge has behaved as a spreading of wave switches to a not spreading of corpuscle, and this switch continues with a very high frequency between the 2 particles. So a free electron has no time to run too far away between 2 boson exchanges, and the model sketched by us may offer an explanation for the more than 300 years old dilemma of the wave corpuscle duality, not only in the case of the electric charges, but also for other field charges in other interaction fields. The third thing which I would like to discuss here is the interpretation of the electric movement. If we look at the lines 3 to 5 of the extended Dirac equation, you find here a white marked component. This is an extension to the electric moment of the interacting charges. The rest is responsible for a magnetic charge, magnetic moment, but we will not be this now. The electric moment is interesting for us because Dirac neglected the existence of the possible existence of an electric moment in his original theory. So he said that this is the only imaginary component of his equation, and there should not exist that means that we don't need to deal with it. He referred to Wolfgang Pauli, that Pauli wrote 2 years ago that we don't have any electric moment. But there is a little problem here, because this sigma, which is a vector of the 3 components of the spin, has a second component. The second component of the spin is imaginary in itself. And if we multiply an imaginary component with I, we will get a real component. And this has never been discussed in textbooks on quantum electrodynamics. So what is here, we can mark with an N and D, because it is a contribution of the D field, and these components we will mark with M. This is the component, a contribution to the magnetic moments, and the ND and ND, that means the magnetic extensional and the electric extensional component, can be regarded as magnetokinetic and electrokinetic moments of the theory, and they appear in the theory due to the additional freedom of the system. So how can we interpret the electric moment what was neglected by the classical Dirac theory? In the classical Dirac theory, there appeared only this component. But now we have the sum of these two components, and we can handle this. because the sum of the wave terms, which can be considered as the full dielectric moment, can be handled that we make its imaginary terms equal to 0, and from these simple differential equations we can calculate the components of the kinetic field, the D field, and its real terms will provide us measurable quantities. So we got something measurable physical quantity which we can use in our material physics experiments and measurements. Let's see the last part, the last consequence that I would like to discuss in my lecture, the quanta of the kinetic gauge field, what we call the dyons. So the dyons that I mentioned mediate the exchange of isotopic electric charge spin, and they appear in the presence of they are the quanta of the D field, and they appear as a consequence of the the conservation of the second order delta, which is has such a form. This second part shows a good gauge term, which shows that this is a gauge theory which is subject of the second current. And the force component of this current, the GD4, provides the isotopic electric charge spin density of the system but demanding. Delta, if we replace the form of GD4 here under the integral, this GD4, the general G current, it doesn't transform as a vector. But this delta, the isotopic field charge spin, transforms as a vector under rotations in the isotopic electric charge spin field. So these delta, uppercase delta, are the quanta of the day field for electromagnetics, and they can be obtained by replacing the expression of the force component of the G in the vector integral in such a form, and these delta electrons are the electromagnetic delta are the sources of the quantum, this new quantum of the electromagnetic field in interaction with the D kinetic gauge field. The conservation of the uppercase delta guarantees the invariance of the computation between the two isotopic electric charge densities. This complementary invariance restores the symmetry that was lost when we replace the general rho charge with the kinetic and the potential charge densities in our physical equations. So the delta electromagnetic means the isotopic electric charge spin, which is the charge of the D kinetic field, is mediated by the lowercase delta, the dyons, and the Feynman diagram of such an interaction can be written in this form. So there are two charges which interact, the Coulomb-like and the current-like charge, and they exchange parallel or probably anti-parallel two dyons, a photon and the dyon, which is marked by delta, and they switch their states, isotopic change, and the Coulomb-like charge will move further as a current-like charge, and the current-like charge as a Coulomb-like charge. So, the dyons as bosons mediating the electromagnetic interaction together with the photons appear as boson pairs of the photons. The Coulomb charges are and the kinetic Lorentz charges compose fermion-fermion pairs, the photons and the dyons compose boson-boson pairs, and this is an alternative of the fermion-boson and boson-fermion pairs described by the Suzy model, There is another difference that we don't need to demonstrate the fermion pairs of the existing fermions because they are the isotopic states of each other, like the gravitational mass and the inertial mass and so on. So there are left the 13 new bosons which should be demonstrated and should be found by experience. We know very few about these bosons. We know only that their mass depends on the energy or the velocity of the kinetic particle which moves, and this boson will exchange the difference between the Lorentz-boosted mass and the rest mass of the particle. That means that at very high energies, the mass of this boson should be much times larger than the rest mass of the fermions in between them they radiate. So this theory predicts similar means for the other models as well. And this is my final conclusion, but you can read here, but my time is over, so I stop here. Thank you for your attention. Have you any questions?
The standard model has two kinds of masses. The X-man uses the mass, includes the mass of the elementary particle. That means the elementary particle is the quarks and leptons, and also the weak boson. At the same time, the mass of all such objects is mostly the proton mass, which is essentially kinetic light in some sense, because it is caused by the gluon content and the interaction between the quarks, whose mass adds only at 2%, maximum 10%. How the mass plays a very important role in the theory. How these two masses attribute. Can you repeat the question? So the question is, So the question is how the two kinds of masses they are differentiated or attributed for in your theory. The mass caused by the X-norms, which is the elementary particles mass, and the mass of the proton and the neutron, which is essentially energy.
So two things. This theory leaves the mass of the standard model bosons intact, and all differences in the masses are thrown to the new boson. There is there is an exchange of these ions parallel with the ions as well, parallel with the weak bosons as well, not only parallel with the photons and the gravitons. So there is an open question: how will this theory, if it will be proved correct and proven by the nature, give an answer to the question of the dark matter. So there are different, but at least three groups of explanations for the dark matter, and according to this model, most of them, at least in high energies, most of the masses are always moving between the protons and neutrons color charges. If we have another ionic diode, which is exchanged between the color charges according to this model, then there is a mass exchange between the color charges. And even if they are confined in a very small volume, but they can move very fastly within this small volume, and there is an acceleration for each particle, and so they can acquire high velocities. That means they exchange high masses through the ionic diodes. And so most of the mass is on the way always by these bosons, but we never detect